Now that we have discussed the different aspects of IPv4 addressing, let us today concentrate on the IPv4 header. Now we have seen that whenever a packet arrives from the transport layer to the network layer adds its own header information. Because there are two versions of IP, the IP version 4 and IP version 6, and both have different types of header information, today we'll concentrate on the IPv4 header. Now this is a typical IPv4 header. We'll discuss each of these fields in detail. These two fields, source IP address and destination IP address, we have already discussed in detail along with subnetting. So to understand these two fields, I'll advise you to go through the previous two lectures. Now the IPv4 header is a variable size header field because there are options. If you remember, there are options in the transport layer also in the TCP. Similarly, the IPv4 header also contains certain options. These are optional. That means options can be present or absent. If options are present, it can go up to 40 bytes. Apart from this, there are other fields which are always there in the IPv4 header. Now we'll discuss each one of these header field one by one. Let us start with the first field, which is shown as version of size 4 bits. Now this version, which is of 4 bits, this specify the IP protocol version. Now as we have already mentioned, there are two versions of the IP protocol, IP version 4 and IP version 6. Because we are discussing the IP version 4, so the value of this particular header field is 4. So in binary, this is 0100. That means in a IPv4 header, this particular field of 4 bits will always be 0100, a value of 4. Now be clear about this, that if you insert a value of 6 in this header field, it does not make it a IPv6 datagram. The IPv6 datagram is a completely different type of datagram with a different structure. So the value in this field in IP version 4 will always be 4. It cannot have any other value. It cannot even have 6, because that does not make it an IP version 6 datagram. So the first header field in IPv4, which is named as version, it will contain a value of 4. Next, we'll discuss the next field, which is known as header length. Now if you look at the name header length, that means it simply keeps the information about the size of the header. Now why do we require this information? We require this information because the header size is variable. If the header size had been fixed, we would not have required this field. Now because the header size is variable, because of these options fields, that's why we should know where the data starts. So we have to specify the header length. Now this header length, which is very popularly shown as HLAN, is of 4 bits. Now we have already seen why do we require, because there is an options field. Now the options fields can vary between 0 to 40 bytes. That means when option field is not there, then the size of the option field is obviously 0. Maximum it can go up to 40 bytes. Clear? So the without option size, the header size would be 20 bytes. So if this option field is not there, this size, the size of the header from version to up to this destination IP address, this is 20 bytes. Clear? Options can vary from 0 to 40. So if I have the maximum available data in the option field, then the size of the header would be 20 plus 40, 60 bytes. So the maximum size of a header would be 60 bytes. Now when we provide a value in this HLAN field, it uses a scaling factor of 4. Remember, we are using only 4 bits to specify the size. That's why a scaling factor of 4 is used. So whatever be the header size, the total header size, without option this is 20 bytes, with full options this is 60 bytes. So whatever be the header size, this is divided by 4 to get the value of HLAN. Alternatively, if the value of HLAN is given, we can find the total header size or the header length just by multiplying it with a factor of 4. So for example, these are different HLAN values. So if I have no options field, then in that case the header size or the header length is 20 bytes. Now what will be the value of HLAN? The value of HLAN would be header size. The header size is 20 bytes without options divided by 4. This is a value of 5. So 0101. So if I go back to the header field, so this field will have a value of 0101 if option field is not there. If option field is not there, then the header length field, the h-length field will contain the value 0101. If we have the full options field, that means full options is there, then the header size is 60, 20 bytes of the normal header size plus 40 of options, that is 60 bytes. So in that case, the value of h length is the header size, which is 60 bytes divided by 4 is 15. So the maximum value in h length 1111. Whenever option field is there in full, then the h length field will have a value of 1111. Now alternatively, if we are given a h-length value, so say the h-length value contains a value of 1001. So if we are asked to find the header size, it's very simple. The header size would be this value multiplied by 4, 36 bytes. That means 20 bytes of normal header plus 16 bytes of options. So when the h-length value is 9, then we can simply find the header size to be 36 bytes out of 20 bytes of normal header and 16 bytes of options field. So we have discussed the header length also. Next we will discuss the type of service field. The type of service field, popularly shown as TOS, this field was introduced in IPv4 to allow different type of IP datagrams to be distinguished from each other. Now what is the meaning of it? The people who developed IPv4 initially thought that because different applications have different requirements. Now say one particular datagram has data of an applications which is sending data of real-time data, say some match is being telecast live, so that datagram contains that type of data. In another datagram, some other type of data is sent where the priority is less, that means it does not have to be delivered in real time. So basically if we look at it from the transmission of point of view, if a datagram contains say data of real-time application, then obviously this type of data should be given priority. So an intermediate router, if it receives a datagram which contains real-time data, this particular datagram should be given priority over a datagram which does not have data which will have non-prioritized data. So how do we distinguish between this different type of datagrams? So initially this field was introduced to differentiate between these different type of datagrams, so that the intermediate routers can give preferential treatment to some sort of datagram over some other datagram. But in reality, in most of the cases, the intermediate routers do not give any sort of priority to any datagram because in most of the cases the routers do not know what type of application layer data that datagram contains. That means almost all the intermediate routers would provide a first come first served sort of service to the arriving datagram. So this particular field, the type of service field, was not used for its intended use. The intended use was to provide differentiation between different datagrams carrying different type of data, but this sort of preferential treatment was never provided to this datagram. So the original aim of this TOS field was never achieved. Now these days this particular field is used for differentiated service. Mostly it is used for providing quality of service. Quality of service is basically defined as say having the minimum requirement to provide a better quality. That means say if two persons are talking, using the internet, so say a dedicated bandwidth is required for transmission of the audio and video. Say a dedicated bandwidth of X is required. Now if that dedicated bandwidth is not available, say sometimes the bandwidth goes down from Y, in that case the quality will degrade. So to maintain a minimum standard so that the quality of service is maintained, to achieve such a thing, this particular field is used these days, the type of service. We'll discuss the this type of service field in detail as it is being used today in a separate lecture when we'll discuss multimedia networking. So as of now, simply understand that the original intention of type of service was to provide a mark on the datagrams which would give a chance to the router to provide preferential treatment on certain datagrams, but that particular idea was never implemented in internet. Now let's go to the next field, the datagram length. The datagram length, a 16-bit field, is basically the size of the whole datagram. This includes the header as well as the data. So the datagram length is the total length of the IP datagram. It's header plus data and measured in bytes. That means whatever value is there in the datagram length field, that number of bytes is the size of that particular datagram. Clear? So since 16 bits are used, so the maximum size of a datagram can obviously be of 2 to the power 16 bytes, which is 6553 bytes. 20 bytes of regular header field. If options is there, option field of maximum up to 40 bytes. So 60 byte of maximum header information plus data. The maximum size of the IP datagram can be theoretically up to 6553 bytes. Why up to this? Because 16 bits are used to indicate the datagram length, and by using 16 bits we can represent a maximum value of 6553 bytes, and this datagram length is measured in bytes. Though the size of a datagram can be of maximum 6553 bytes, in reality the datagrams are never this much bigger. Why? I hope you remember MTU from our discussion in transport layer. There is something called MTU in the underlying layer, the data link layer. So because there is a restriction of the amount of the size of a frame that can be transmitted in the data link layer, that's why a datagram cannot exceed this particular MTU. So the size of a IPv4 datagram will depend on the size of MTU. If the MTU is say 1500 bytes, if the MTU is of 1500 bytes, say for example, in that case the datagram cannot be of a size bigger than this. Clear? It cannot be a size bigger than this. Remember, a datagram has to be sent to the data link layer next. Now the data link layer will add its own header. That means some extra information will be added in the data link layer also. So the combined size, the final size should not exceed this MTU. So whenever a datagram is created, it should be ensured that it does not exceed the MTU, while also taking the fact that some amount of header information will be added in the data link layer also. Next, this field identifier 3 flags of 1 bit each and a fragmentation offset. These fields are together involved in an issue called fragmentation. We'll discuss fragmentation in detail after we discuss the other header fields. So let's keep off this as of now, and then let's go to the next header field, time to live. TTL or time to live is an indication of a time that the datagram is allowed to exist on the network. That means the TTL will have a value, and that value will say to what amount of time that datagram can exist on the network. Say for example, this host A is sending some data to B, and there are many alternative routes from A to B. There is this route, there is another route which goes through this, there is an alternative route. Now say a datagram is moving from this router to this router, and depending on the routing path, the best routing path, it can flow through any path. Now because the routing path is decided by routing algorithms, due to some malfunction in the routers, or due to some malfunction in creating the routing table, it can happen that a wrong routing path is prepared, a wrong routing table is prepared, and for such a reason it may happen that by mistake a datagram is moving around in a loop in this network. Say for some reason this datagram comes to this router, then it goes to this router, then it goes to the routers, again come back to the router, and it is moving around this router for a long amount of time in a loop because of certain malfunction. Now what will happen? Because of this datagram is moving around, this would be unnecessarily creating traffic in the network. Clear? So this time to live field is included to ensure that the datagram do not circulate forever in such circumstances in the network. So what happens is this particular field, TTL field, a particular value is inserted in this TTL, and every time the datagram visits an intermediate router, the value is decremented by a value of 1. But say a datagram is created and from A it starts traveling. So say just for an example, the TTL value is initial TTL value is given, say the value is 50. Say a value of 50 was inserted in the TTL field. Now what happens is when the datagram first arrive in this router, it will be decremented by a value of 1. So 50 minus 1 becomes 49. Next it comes to the next router, another one is decremented, it becomes 48. Next router 47, and so on. So every time it visits an intermediate router, the value is decremented by 1. If such a circumstances arise that the value becomes 0 in some intermediate routers before arriving at the destination, that particular datagram is discarded in that router itself. So say for example this particular datagram went into a loop for certain malfunction in the network. So every time it is going to a router, that value is decremented. So here it becomes 47, then next 46, 45, 44, 46, like this when it is in the loop. And at that point of time when it becomes 0, that particular datagram is discarded. Clear? If the datagram arrives at the destination, then it should ensure that it arrives at its destination before the TTL becomes 0. Clear? So this TTL value, once the value reaches 0, that particular packet or the particular datagram is discarded in that router where the TTL value became 0. Now the default TTL values vary within different operating systems because it uses 8 bits. So the maximum value of TTL would be 2 to the power 8. The maximum value of TTL would be 2 to the power 8. But this huge number, this bigger number is rarely used. 2 to the power 8 would be 255. So this 255 value is rarely used when using TTL. Normally by default a value like 64 is used. A 64 value is used. So it is an indicative that a datagram should arrive at the other end within 64 hops. But in reality, it is expected that a datagram reaches the other end within 30 hops. So a base routing table would be a routing table which ensures that a datagram reaches the other end within 30 hops. So if I want to achieve that a datagram reaches the other end within 30 hops, I should initialize the TTL value with a value of 30. So within 30, that particular datagram will reach the other end. If it does not reach the other end, if the TTL becomes 0 in an intermediate router, that particular datagram will be discarded in that datagram itself. This is just a pictorial representation where a particular datagram was initialized with a value of 255 in the TTL field. So in the first router it became 254, in the next router it became 253, in the next router it became 252, and then it arrived at the destination. So in this case the particular packet arrived at the destination much earlier than the TTL. Clear? So after TTL we'll come to the next field, which is upper layer protocol. Now this upper layer protocol is a glue which binds the transport layer and the network layer. So we have the transport layer, a packet is coming from the transport layer to the network layer. So this upper layer protocol header field, is that glue, is that part which actually binds the transport layer to the network layer. Remember, whenever data come from the application layer to the transport layer, what was the part that binds the application layer to the transport layer? If you remember, it was the port number, the destination port number basically. So that means the destination layer told that to what application that particular package belongs to. In the same manner, the upper layer protocol field tells to what protocol that particular packet belongs to. A packet is sent from transport layer to network layer. Now that packet could have either come from TCP or it could have come from UDP also. So a particular value is inserted in this upper layer protocol header field to indicate to which upper layer protocol this particular packet belongs to. Clear? So UDP by default has a value of 17, TCP by default has a value of 6. So if I put the value of 6 in the upper layer protocol field, that means that particular packet which came from the transport layer to the network layer belongs to TCP. It was delivered from the TCP protocol. If it has a value of 17, that means that particular packet was delivered from the UDP protocol of the transport layer. Next we go to the header checksum. We already know what checksum is. Checksum is used for detecting errors. Okay, so header checksum, as the name indicates, is a checksum calculated on the header data only. That means the checksum is calculated on the header information, not the data part. We have already done checksumming in the transport layer, so the same algorithm that was used in the transport layer is used in the network layer also. Remember the algorithm, 16 bits, all the data in the header is divided into 16-bit words. All the 16-bit words are added together, carry, if there is a carry, it is wrapped around, and the final result is one complemented. If you remember the algorithm which we discussed in the transport layer, it's the same algorithm. If you do not remember, please go back to the checksum calculation in the transport layer. It's the same algorithm. The only difference is in this network layer, while calculating a checksum, the data part is not used, only the header part is used. And once the checksum is calculated, it is inserted in this particular field, the header checksum field. Now the other difference with checksum in the transport layer and in the network layer is that in the transport layer, the checksum is calculated in the source and then it is verified in the destination. That is, only two nodes are involved, the source and the destination. The source calculates the checksum, and the other end, the destination side, it verifies whether the checksum is correct or not. But in network layer, the checksum is calculated in every intermediate router. So this header checksum is recomputed at each intermediate router. Now, why do you think the header checksum is recomputed? It is recomputed because a particular field changes in every router. And what is that field? We have already seen that field is TTL field. The TTL field changes at every intermediate router. It is decremented. So when the TTL field changes, that means the checksum will also change, because every header field is used to calculate the checksum, and because the TTL field changes, that's why the checksum has to be recomputed and reinserted at every intermediate routers. Clear? Now remember, whenever any miscalculation is seen in the intermediate routers, whenever a router sees that there is something wrong in the checksum, it will discard those particular datagrams. Clear? So this is header checksum. Now the next two header fields, source IP address and destination IP address, these two we have discussed in detail in the previous two lectures. So if you have not gone through the previous two lectures, I'll advise you strongly to go through these previous lectures to understand the IPv4 addressing scheme. Okay, now we'll come back to the fragmentation part, all these fields which are involved in fragmentation. Now we have a 16-bit field which is known as identifier, we have a 13-bit field which is known as a fragmentation offset, and apart from that we have three flags, three 1-bit flag. One flag is always set to 0, that means this flag is not used. Okay, there is another flag DF which is known as do not fragment. We'll see what does it mean. And MF normally means more fragments. We'll see the details of each of these fields. So a 16-bit field, a 13-bit field, and three flags. Out of these three flags, one flag is never used. There are two flags which are used in this process known as fragmentation. Now what is the fragmentation? The normal definition of fragmentation is it is the breaking of a datagram into small number of pieces which are later reassembled. That means a particular datagram which is divided into smaller number of datagrams. Okay, now this smaller number of datagrams are individual IPv4 packets. Clear? So that means it is not that a particular datagram is taken and is divided. It means more IPv4 packets are created from this datagram. The data part is divided into these other smaller datagrams or smaller fragments. Clear? The header information will always be there in every datagram. So fragmentation, it involves breaking a datagram into small number of pieces, and these are later reassembled at the destination. Clear? Now whenever fragmentation happens, whenever a datagram is divided into smaller packets, wherever it is done, fragmentation is done by intermediate routers. In whatever intermediate router it is done, the reassembly, those fragments has to reassemble. That reassemble is not done by any intermediate routers. The reassemble is done at the destination only. Okay. Now the first thing we should understand is why fragmentation is required. To understand why fragmentation is required, we come back to that particular information which we have discussed previously, known as MTU, or maximum transmission unit. This particular fragmentation is an occurrence in IPv4 because of the existence of MTU, or maximum transmission unit. Now remember, the next layer is data link layer, and there are different data link layer protocols. There exist different data link layer protocols, and each of these different data link layer protocols can handle different sizes of frames. That means whatever technology is used, every technology can accommodate different size of maximum, different frames of different sizes. That means if I have, say, example, Ethernet technology, Ethernet can handle up to 1500 bytes of frames only. That means if I have a frame of, say, 4000 bytes, Ethernet will not be able to handle that particular frame. Some of the wide area links can handle not more than 576 bytes. Some technologies such as SONET and all, they can handle a bigger size of frame. Now the maximum amount of data that a link layer frame can carry is known as maximum transmission unit. So MTU is defined as the maximum size of the frame that can be handled by the underlying data link layer. Now why this is important? This is important because assume that a datagram is created of a size and the underlying MTU is much less. Say a datagram is created of size 5000 bytes and the underlying M2 is of 1500 bytes, and obviously the datagram cannot pass through that particular MTU. If I have a small size door and if I try to push a huge size of packet that exceeds the door, that packet cannot pass through the door. I have to open the packet and divide into smaller parts, then only I can pass those smaller parts through the door. So fragmentation is a similar process. A particular datagram is divided into smaller parts. Each of the smaller parts are known as fragments. Okay, so fragmentation is an internet version 4 process. Because we'll later see that internet version 6 does not support fragmentation. So fragmentation is a process that breaks datagrams into smaller pieces, and each of the smaller pieces is known as a fragment. So why do we do fragmentation? Because so that the resulting fragments can pass through the data link layer, which has a smaller MTU than the original datagram. Okay, and as we have mentioned, this reassembly is done at the receiving host only, not in the intermediate routers. Now, once there is a requirement of fragmentation, these different fields which we have seen are used. First is the identifier. So this field identifier is used to identify the fragments of one particular datagram. That means if a datagram is fragmented into, say, 10 smaller fragments, each of these 10 fragments will contain the same identifier so that it can be easily identified at the other end. So all the 10 fragments that was created from the original datagram, each of these 10 fragments will have the same identifier. So the same identifier will say that each of these smaller fragments belong to the same original initial fragment. By using the identifier, we can tell the receiver that they belong to the same fragment. But I have to also tell about the order, that this is the first fragment, this is the second fragment, so that they are reassembled correctly. So for that, the other fields are used. Now let's see how they are used. And now say again the same example, a particular frame or a particular datagram was fragmented into 10 smaller fragments. Now for all these 10 fragments, the identifier will be same. For the last fragment, okay, so 10 fragments were created, fragment 1, 2, 3, 4 like this up to fragment number 10. In the last fragment, the MF field, the MF flag bit is set to 0. Clear? And for the other fragments, this MF bit is set to 1. So this MF bit is 1 for all fragments other than the last fragment. The last fragment is set to 0. That means whenever this particular fragment with MF set to 0 arrives, the receiver knows that this is the last fragment. Okay, and whenever a MF is set to 1, the receiver understands that more fragments are coming. Clear? So MF set to either 1 or 0. If it is set to 1, that means there are more fragments. If MF is set to 0, that means this is the last fragment. Now another important thing is a scaling factor of 8 is used for the last field, which is known as fragmentation offset. Now what is fragmentation offset? Fragmentation offset field is used to specify where the fragment fits within the original IP datagram. So till now what we have done, we have created some smaller fragments, we have given them the same identification number, so the receiver knows that they belong to the same fragment, so they can be reassembled together. Now when it receives a fragment with MF0, that means this is the last fragment, and for all the other fragments where MF is set to 1, that means these are other fragments than the last one. But I have to reassemble them in the correct order. The first fragment should be at the first place, the second fragment should be at the second place, the third fragment should be at the third place. How do we do that? We do that by using this fragmentation offset field. So this fragmentation offset field will specify the position of that fragment in that complete datagram. Now for this fragmentation offset, a scaling factor of 8 is used. Now let us understand this process using this example. Now say this host is A, this is sending some data to B. Okay, now A initially create a datagram which has the size of the datagram is 4000 bytes. A 4000 bytes datagram was created. Say there are no options, so it means there are 20 bytes of header. 20 bytes of header is always there, and under 3980 bytes of data. So I have a datagram which have a header of 20 bytes. There are no options, 20 bytes of header and 3980 bytes of data. Total the size of this datagram is 4000 bytes. Now there are several alternative paths from A to B. It can go through this path, it can go through this path, it can go through this path. There are different paths available, and assume that as of now this is the path shown in the red color. The packets are flowing through this path. The routing algorithm has decided that this is the most suitable path. Now the MTU of each path is shown. So after it arrives in the first router, the MTU is 5000 bytes. Next the MTU is 6000 bytes. Then MTU is of 1500 bytes, MTU is of 6500 bytes, and MTU is of 5000 bytes. So the 4000 bytes datagram arrives from A to this first router. Now the MTU is 5000 bytes. That means the 4000 bytes of datagram can easily pass through this particular MTU. Next it arrives in the next router. Now the MTU is 6000 bytes. It is a bigger size than this 4000. So 4000 can easily pass through this 6000 byte MTU. Now it arrives in the third router, and in the third router the MTU is 1500 bytes. Now this 4000 bytes of datagram cannot pass through this router because of the smaller size of MTU. So at this router, fragmentation has to be done. This packet has to be divided into smaller parts so that these smaller parts can flow through this MTU of 1500 bytes. Now one important fact here is that because we are using a scaling factor of A, we have already seen that in fragmentation offset we use a scaling factor of 8, and because of this reason we should ensure that whenever we create fragments, the amount of data inside the fragments has to be a multiple of 8. That means it should be divisible by 8 except the last fragment. The last fragment can contain any amount of data, because that will not be used in calculating the fragmentation offset. We'll see that later on. But as of now, understand that the amount of data that can be placed inside a fragment should be a multiple of 8. For example, say assume that my MTU is 430 bytes. My MTU is 430 bytes. That means I can pass a packet, I can pass a datagram of size 430 bytes. So if I say I have a datagram without options, that means I have 20 bytes of header. If there are 20 bytes of header, how many data I can insert? I can insert data of 410 bytes. So 410 bytes of data plus 20 bytes of header, 430 bytes of total size. The datagram is of 430 bytes. This can pass through an MTU of 430 bytes. But 410 is not divisible by 8. This is not a multiple of 8. So I cannot insert data of size 410 bytes. I have to insert a value which is divisible by 8, say 400. So I should ensure that the amount of data should always be divisible by 8. So in this example, the size of this datagram is 420 bytes. This can pass through this of MTU of 430 bytes. I could have created a packet of 430 bytes, but because that data part would not have cannot be divided by 8, that's why 410 bytes was not used. Instead, 400 bytes was inserted in the data part. So for the remaining 10 bytes, I have to create another fragment. Clear? The last fragment, the data in the last fragment need not be divisible by 8. Now let's go back to this process. So this 4000 bytes datagram arrive in this router with an MTU of 1500 bytes. Now the particular datagram has to be divided into smaller parts. Now when it is divided, first let us see how many datagrams, how many fragments are required in this particular example. So now here the MTU is 1500 bytes. That means a datagram can be sent which is of size 1500 bytes. Now the header size is 20 bytes. Remember, this header would be there in every datagram because every datagram is also an individual IPv4 packet. So every packet will be of size, every fragment will be of a particular size where the header size will be 20 bytes. So how many bytes of information can I insert in the data part? I can insert 1480 bytes. Why 1480? Because 20 bytes of header, so 1480 plus 20, it makes 1500 bytes. So in each fragment I can insert up to 1480 bytes. Now I will also have to see whether 1480 is divisible by 8 or not. Remember, it should be divisible by 8 for all the fragments except for the last fragment. Luckily 1480 is divisible by 8. If I divide 1480 by 8, I get a result of 185. So I can insert 1480 bytes of data in each of the fragment. Now how many fragments are required? Because there are total 3980 bytes of data. So I can simply calculate how many fragments I require. So 1480, another 1480 will give 8, 16, 8, 9, 3. So 3 fragments will be required. Clear? Very simple. 1480 bytes in each fragment. So 1480 bytes in the first fragment, another 1480 bytes in the next segment, and a few amount of remaining data in the third fragment. So 1380 bytes divided into 3 fragments. So 3 fragments I required to create using fragmentation. So now these are the different values after I do my fragmentation. So I require 3 fragments: fragment 1, fragment 2, fragment 3. First fragment will contain 1480 bytes of data. Second fragment contains another 1480 byte of data. Remaining, because total there were 1380 bytes, remaining 1020 bytes of data, this will be inserted in the third fragment. Now remember, all these three fragments should have the same identifier. Assume that the identifier is 1501. Okay, assume it can be anything. So assume that the identifier is 1501. So this particular identifier will be used in all these fragments. By looking at this identifier, the receiver side will understand that all these fragments belong to the same original datagram. Come to MF flag. The last fragment will have this MF flag set to 0. Clear? And the other two fragments will be set to 1. This we have already seen. All the fragments except the last one will have the MF flag set to 1. The last fragment will have its MF flag set to 0. Now come to the fragmentation offset. The fragmentation offset uses a 8 scaling factor of 8. Now the starting datagram, starting fragment will have a fragmentation offset value of 0. 0 means this is my first fragment. So whenever I receive the fragment which has a fragmentation offset of 0, this means this is the first fragment. Clear? Now, how many bytes are there in this? There are 1480 bytes. So if I count the bytes starting from 0, 1, 2, 3 like that up till 1479 bytes are there in my first fragment. Clear? First byte number 0, then byte number 1, byte number 2 up till byte number 1479. So this number of bytes are there in my first fragment. The offset 0 indicates that this is my first fragment. Clear? Go to the second fragment. Where does my data start? My data start at byte number 1480. Okay. So how many bytes are there? Total 1480. The first byte number is 1480. This is the fragmentation offset of my second fragment. Clear? So the fragmentation offset here, it should have been 1480, but because it uses a scaling factor of 8, so I have to divide it by 8. When I divide it by 8, this is 185. So the fragmentation offset of my second fragment is 185. So my second fragment starts at byte number 1480. And how many bytes does it contain? It contains 1480 bytes. That means another 1480 bytes. So it goes up to 2959. Okay, from 1480 bytes it will go up to 2959 number of bytes. Why 2959? Just simply add 1480. 1480, it starts with 1480. And I have 1480 bytes of data, so that means I add 1480. Clear? So if I add 1480, so 8 plus 16, 1, 9, 2960. So since I start from 1480, it will go up to 2959. So my third fragment starts from 2960. My third fragment starts from 2960. And how many bytes of information will be there? There will be 1020 data bytes. Clear? In the third fragment, starting from 2960, total 1020 data bytes will be there. So what will be the offset of my third fragment? My offset would be 2960 divided by, because it uses scaling factor of 8, 2960 divided by 8, which is 370. Clear? So this fragmentation offset will give the position of the particular fragment in the total datagram reassembly. So when I reassemble my original datagram, just by looking at the fragmentation offset, I can understand that where does that particular fragment fits in. Clear? So I can fit the fragmentation in its correct order just by looking at the fragmentation offset. And whenever I see that MF flag is set to 0, I understand that this is the last fragment, and after that no more fragments are there, and I can stop the reassemble then and there itself when I reach a fragment with the MF flag set to 0. Clear? Let's do another example. A datagram size of 1440 bytes arrived at a router with an MTU of 576 bytes. So datagram size is 1440 bytes. So there are no options. So 20 bytes of header and 1420 bytes of data. And the MTU is 576 bytes. The original identification number is 177. That means all the fragments will be stamped with this particular identifier 177. So the MTU is 576 bytes. So now first I have to see how many fragments are required. So you do all the mathematics and then you will find that 3 fragments are required. 3 fragments are required because the size of M2 is 576 bytes. So 576 bytes means 20 bytes of header information. Okay, so yeah, you have to subtract 576. The total size is 576. Out of that 20 bytes is header. So 556 bytes of data. 556 bytes of data has to be there in the fragments which are created. Clear? Now here is the important part. Because the MTU is 576 bytes, I can pass a datagram of size 576 bytes. 20 bytes is header, so the data part can contain 556 bytes. Now remember, this data part has to be divisible by 8. For all fragments, it has to be divisible by 8 except the last fragment. And if you look at it, 556 is not divisible by 8. So although I can insert 556 bytes in my fragments, I cannot use 556 because it is not divisible by 8. So the nearest number that is divisible by 8 is 552. Clear? If you look see the calculation, 552 is divisible by 8. So instead of 556 bytes in my datagrams, I have to insert 552 bytes because 552 is divisible by 8. So if I can insert 552 bytes in one fragment, how many total fragments are required? Again, there are total 1420 bytes of data. So I require 3 segments, 552 bytes in one fragment, 552 bytes in another segment, and the remaining 316 bytes in the final segment. So these 3 together will give 1420 bytes. So total 1420 bytes divided into 3 fragments, and each of these fragments contain 552 bytes except the last fragment. The last fragment will contain the remaining byte. The identifier would be same for all the fragments. MF flag set to 1 for the first fragment, 1 for the second segment, and 0 for the last segment. Now come to the fragmentation offset. First one, the fragmentation offset is 0 because the first fragment. So what were the bytes in the first segment? It starts from 0 up to 551. Total 552 bytes. So from 0 up to 551. So this is the first fragment. The next fragment starts from byte number 552. So my fragmentation offset of my second fragment should have been 552, but because we use a scaling factor of 8, so I divide 552 divided by 8, the value is 69. So the fragmentation offset is 69. Again, another 552 bytes is there in this. Okay, another 552 bytes. So I add it. What do I get? 2 plus 2, 4, 5 plus 5, 10, 11, 1, 1, 0, 4. Clear? So again, I divide it by 8. Whatever value I get, this is the third, this is the fragmentation offset of my third fragment. So this is how we proceed. Clear? I hope fragmentation is clear, and given any situation, you should be able to fragment and find the related values. The most important is obviously the amount of data which you insert. Remember, it has to be divisible by 8, and once you insert the data, finding the fragmentation offset is fairly easy. And then you have to set the MF flags. Basically, you have to set the MF flag as 1 for all the fragments except the last one, and in the last one the MF flag should be set to 0. Clear? Now remember, there was another flag which was shown as DF, this particular flag. three flags. MF flag we have discussed here, it is set either to 1 or 0. Now DF flag, DF indicates do not fragment. So if this flag is set, DF flag is set, that means do not fragment under any circumstances. So in this example, come back to this example, if here I would have set DF equal to 1, okay, if I have set DF equal to 1, that means do not fragment this packet even if it is required. That means whenever this particular fragment arrives in this router, and because it cannot pass through this router, because the MTU is 1500 bytes, now it has to fragment, but because DF flag is set, that means do not fragment, so this router does not perform any fragmentation and it will discard this packet. Clear? Later on, this particular host would has to send datagram with smaller size. That means next time when it sends those datagrams, it has to create datagrams of smaller size so that these particular datagrams can pass through this router which has a smaller MTU. How does it know about the size of the MTU of an intermediate router? This is known by using another protocol which we will later on see. Whenever we use ICMP, a protocol known as ICMP, that will help it to know the size of the MPU of some intermediate routers. Okay, so the main idea is that whenever DF flag is set, it indicates that that particular datagram should not be fragmented. And because this fragmentation, whenever you have to create fragmentation, it adds some more work for the router. That's the overhead for a router. A router has already many tasks associated with it. We have already seen it has to do forwarding, it has to do routing, it has to recalculate checksum. Apart from all these things, if it has to also perform fragmentation, it creates a more overhead for that router. So to ensure that this overhead is not given to these routers, IPv6 has in fact done away with fragmentation. Later when we see the IPv6 header, we'll see that IPv6 has completely discarded fragmentation. It does not allow fragmentation. So whenever such a situation arises, whenever the packet cannot pass through a link because of the MTU, in that case the original host has to create datagrams of smaller size so that it can pass through that particular router with a smaller MTU. So IPv6 ensures that fragmentation, this particular fragmentation is not done by routers. It has completely discarded this particular idea of fragmentation. Clear? Now let's see some examples. The first example is an IPv4 packet has arrived with the first 8 bits shown as this value 01000011. The receiver means the final destination, discards the packet Y. Now if I go back to the header, this is the header. First 8 bits means 4 bits and 4 bits. 4 bits for version and 4 bits for header. Now can you think why this IPv4 packet is discarded? First 4 bits, 1, 2, 3, 4. First 4 bits are for the version number, and next 4 bits are for the header length, the H length. Now if I look at this value 0100, this is the value 4. So there is no problem with this. If I look at this, this is value 0011, that is in decimal, this is the value of 3. Now by looking at this value, can you say why this packet is discarded? Is there something wrong in this packet? Obviously. The next 4 bits, that means this 4 bits shows an invalid header size. Now this is 3. Remember, this has to be multiplied by 4 because it is a scaling factor of 4. It gives 3 multiplied by 4, 12 bytes. Now remember, the minimum size of a header is 20 bytes. Even if I do not use options, the size of the header is of 20 bytes. But if this value is there 0011, this means that the header size is 12 bytes, which is wrong because the minimum has to be 20 bytes. So some mistake has occurred in the datagram. So the receiver discards this packet, this datagram, because it is showing an incorrect value in the header length field. Next example, the h length has a value of 1000, 1000 in binary. How many bytes of options are being carried by this packet or this datagram? So the h length value is 8 in decimal, so 100 is 8. So 8 multiplied by 4 is 32 bytes. Remember, the normal header size is 20 bytes. Apart from options, the regular header fields is of 20 bytes. So because the h-length value is 32 bytes, so 32 minus 12, the other 12 bytes are options. So this packet or this datagram is carrying 12 bytes of options header information. Next one is an IPv4 packet has arrived with the first few hexadecimal digits as shown. So here instead of binary, we are showing hexadecimal, because if I use binary, it will be a very long information. So instead of binary, a hexadecimal value is shown. The question is, how many hops can this packet travel before being dropped? Now first thing you should understand, which header information give this. Which header field will give the information about hop. Remember, it is the TTL. TTL is decremented at every hop. So if I have a value of say 20 in the TTL field, that means it will start from 20, then it will decrement by 19, 18, 17, like that. That means it can flow through maximum 20 hops, not more than that. Whatever the value in TTL, it can go that number of hops only. So in that case, how many hops it can go through? So let us see what is the TTL field. TTL field is here. Clear? So 16 bits here. This is 2 bytes. This is datagram length 16 is under 2 bytes. So this is 4 bytes. Here, from here to here, this is under 4 bytes. This is total 8 bytes. So TTL field starts at the 9th byte. Now this information is important. The TTL field starts at 9 byte. So now come back to our problem. Okay, so we have to now find the TTL field. So remember, we have seen that the TTL field starts in a 9 byte. So first byte, second, third, fourth, fifth, sixth, 7, 8. So this is the 9 byte 0, 1. 0, 1 is a 9 byte. So in this case, the TTL has a value of 1. So it indicates that this datagram, this particular packet, can go through only one single hop, because in the next hop, its value will be decremented to 0. Clear? So to find the TTL field, we skip 8 byte. The time to live field in the 9 byte is 0, 1. This means the packet can travel only on one single hop. Clear? Example 4, this is self-explanatory. A datagram has arrived with a MF bit value of 0. Is this the first fragment or the last fragment or the middle fragment? We all know that when MF value is set to 0, this is the last fragment. Clear? So no doubt about this. Now, do we know if the datagram was fragmented? We do not know this for sure, because say if a datagram is not fragmented, if a datagram is not fragmented at all, in that case also the MF flag is there, the MF flag value is 0. Clear? Only where some datagram is fragmented, in that case the fragments which are not the last one, in that case the MF fragment is set to 1, the last fragment is set to 0. But in datagrams where no fragmentation is done, in those also MF flag is set to 0. So by looking at MF bit equal to 0, we cannot see whether the datagram is fragmented or not. To know whether the data is fragmented or not, we have to see the other information, the identification, the fragmentation offset, all these different values. Clear? A datagram has arrived at an MF value, bit value 1. Is this the first fragment, the last, or the middle? Do we know if the datagram was fragmented? If MF bit is set to 1, that means there will be more fragments. Remember, whenever MF bit is set to 1, it means there are other fragments also. Only when MF bit is set to 0, it means that there are no more fragments. But only with this information, we do not know whether it's the first or second or third or fourth or whatever fragment it is. To know which number of fragment it is, we have to use the fragmentation offset. We have already seen this. Okay, and of course when this value is set, above bit value is set, we know that a fragmentation has taken place. Now these are some of the questions which you should try yourself. Okay, you can try this too and look. So in the first question, the packet is arrived in which the offset value is 100. What is the number of the first byte? Do you know the number of the last byte? So this sort of questions you should try on yourself and try to find the answers. So with this we finish our IPv4 header information. In the next lecture we'll discuss about network address translation, an important topic of IPv4. Till then, thank you.